right, so I'm going to start out by talking about maybe why we care about series in the first place. Okay, so there are kind of two problems that we've encountered in this class. Well, maybe one problem that we've encountered, and another problem that we can maybe imagine. So the first problem is that there are some functions that we can't integrate. Like, for instance, e to the x squared, something like that. So that's an integral that we don't have any methods to integrate. We could do numerical integration, but we don't have a closed form for an integral of that function. So what can we do? Well, we know that polynomials are easy to integrate. So if somehow we could take this thing here and rewrite it in a different way that looks like a polynomial, then we would be able to integrate that function. So that is one issue. A second issue is that we have these transcendental functions. Like e to the x and sine of x, things like that, that we can't evaluate exactly, except at certain points. Like if I were to ask you, what is the sine of 1? Well, you'd probably pull out your calculator and you'd plug it in there and it would give you some decimal approximation. Well, where does that decimal approximation come from? How is your calculator computing the sine of 1? Well, one thing that it's doing in your calculator is it is writing the function sine of x as this infinite polynomial. Is a polynomial-like thing. So it ends up being a power series. So a power series is like an infinite polynomial. And how do these things come about? So the third thing is, and this is another kind of a problem or an issue that we can think about that relates to the other two, is that linear approximation is not that great. And if you think about linear approximation, what is that? Linear approximation is when you take some function, right? And maybe at a certain point, we want to write a function that has the same first derivative. So L of x has the same derivative first derivative as f of x when x equals a. So they have the same first derivative there. But if we get very far away from that center, very far away from a, then the approximation is pretty bad. It's not that great. So the idea is, what if we made a function that not only had the same first derivative as the function, but what if it also had the same second derivative as the function? And what if we could do it one better and have the same first, second, and third derivative at that point? So we can come up with a polynomial that has the same first derivative, second derivative, and third derivative, and we can keep going. And these are called Taylor polynomials. And so a linear approximation is an example of a Taylor polynomial, but that's just a linear Taylor polynomial. So we can come up with a better one. We could do a quadratic approximation or a cubic, and we can keep going. And these Taylor polynomials are a polynomial that has the same first, second, third, fourth, however many derivatives at a certain point, at a certain center. And so, so we can think about these Taylor polynomials can be a solution to our first two problems, because if I can take a function and I can write it using a Taylor polynomial, I can get an approximation of an integral by just integrating that polynomial. Same thing, I can get an approximation of values of the function if I use this Taylor polynomial. And in fact, we can continue to do the Taylor polynomials in an infinite way, and just keep on going with the Taylor polynomials, and we end up with a Taylor series. And the way we think about a Taylor series is we think of this as an infinite polynomial that has the same derivatives as the original function we started with at some center, x equals a, and we'll call that the center of our Taylor series. Okay, and it goes through the process of how to find these Taylor polynomials in the Taylor series in the textbook, so we're not going to get into all of that right here, but that's kind of setting us up for why we care about series. So if I had a power series and I plug in a value for x, I would end up with some kind of an infinite sum. Okay, so for example, we will prove in the textbook, it's proven in the textbook in the section on Taylor series, that e to the x is equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus, and it keeps going like that, okay? So say I want to find like e squared, right? What would I do? So e squared would be equal to 1 plus 2 squared over 2 factorial plus 2 cubed over 3 factorial plus, and so on. And so I have this infinite sum. And so the question is, how do I evaluate that? And a more interesting question, before we even figure out how we could evaluate it, is, does it add up to some number, or does it just go off to infinity? When I add these positive numbers together, do I actually get a number? Well, I expect in this case I probably would, because I'm saying that I'm claiming that it's equal to e squared. So I'm claiming that if I add this up, then I'll get e squared, is what my claim is. So it seems like I'm able to add up infinitely many positive things and get a finite number in this case. And so the rest of this chapter, chapter 10, helps us to understand how we can and when we can get a finite answer to these infinite sums. And so we'll go through and we'll have a lot of tests and things for that. And then the whole point is that we want to be able to build up this idea of a power series so that I can solve problems like integrating functions that I couldn't easily integrate before, or evaluating functions that I don't know, that are transcendental functions that don't have a closed form. I can evaluate them using a power series. Or I can get better approximations of functions than linear approximations. And so these Taylor series are built out of extending the idea of linear approximation to higher and higher derivatives. So that is kind of an introduction to what series are and why we care about them. So on the previous slide, I claimed that e to the x is equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus, and so on, like that. And so what you have there is a power series. And so there's some series notation that you will learn if you read the textbook or if you're in class. I'm going to kind of assume that you know how to write something like this. So this is a sum from as n equals 0 to infinity of x to the n over n factorial. And so then the claim then is that e squared is equal to 1 plus 2 squared over 2 factorial plus 2 cubed over 3 factorial plus and so on. And so the question is, how do I add up an infinite number of things? Or an infinite number of numbers, right? And so, so what we do here is we would look at the partial sums. Okay, and I'm going to graph these partial sums on a vertical number line here. So here's a vertical number line, and I'm going to plot these guys on here. So, okay, so I know that's supposed to be e squared. E squared is about 7.38, so I'll just put, 7, 8, 6, 5, and so on. Okay, so if I plot these partial sums, what is the partial sum? So S0, so the 0th term is 1. S1 is going to be 1 plus 2, so I'm taking the first two items. I guess I could call that S1 and S2. Anyway, it kind of depends on how you decide to count your index. So we'll call them S1 and S2, just for kicks here. So S2 is going to be 3, right? And then what is S3? Well, it's going to be 1 plus 2 plus 2 squared over 2 factorial. Well, what's that give us? Well, 2 factorial is just 2. 2 squared is 4, so it's 1 plus 2 plus 2, so that's 5. So here is S3 is showing up on my number line, so that's S3. What about S4? So it's going to be 1 plus 2 squared over 2 factorial plus 3 squared over 3 factorial. So I can plot that on my, or 2 cubed, good grief. Where did the 3 come from? Should be 2 cubed. So you get 6.33. And so that goes here, and that's S4. S5 will be 1 plus 2 squared over 2 factorial plus 2 cubed over 3 factorial plus 2 to the 4th over 4 factorial. And that gives me exactly 7. Okay, so that is S5. And we can keep going like that. And what we'll see is that these partial sums start getting closer and closer and closer, and they start to converge upon this e squared, which is about 7.38. And so we see them kind of cluster here, and they get closer and closer to that value. And so what we mean when we say that this converges is that we mean that eventually we're going to get within, if I pick a small neighborhood around the value it's converging to, that eventually it will get within that neighborhood and it won't go outside of it. And I can make that neighborhood as small as I want, and however small I make it, eventually I'm going to get inside of that neighborhood around the limit of the sequence. And so these things, when I add them up, this is called a sequence of partial sums. And so we use the sequence of partial sums. So what does it mean to say that that adding up these infinite number of things converges? What we mean is that this sequence of partial sums converge. So eventually, as I'm adding these up, it's going to get closer and closer to some particular number. Okay? And so So I can use that sequence to approximate that value of e squared if I go out far enough. And I can get as close as I want to by just using more and more terms of my partial sum.